Good evening, everyone. Welcome to Manorama Horizon. I am your instructor today, Thomas. Am I audible to everyone? Are you able to hear me clearly? Wonderful. Okay. So today we are here to study a topic, light reflection and refraction. So I hope everyone can see the screen. I'm sharing the screen now. Is the screen visible to everyone? The topic is visible to everyone? Okay. So let's get started. So we are today discussing light reflection and refraction. So let us revise some basic concepts first. Okay. So let's recall, we have understood that light is a form of energy, right? So light is energy and it moves in straight lines. What is the scientific term for this? When we say that light always moves in a straight line, how do we say this scientifically? Can anyone answer? Pop quiz. Can anyone answer? When we say that light always travels in a straight line, there is a term for this. Can anyone tell me? We have studied this before. Anyone? The question is open to everyone. We call it rectilinear propagation, right? We call it rectilinear propagation, which means that light will always travel in a straight line. And these propagations of light traveling in a straight line, we call them rays. These are what we call light rays. And now we are going to understand what happens when these light rays are interacting with matter. There are two main effects we will understand today. We will understand reflection and we will understand refraction. So here is the question: what makes things visible? What makes things visible? For example, if I have, let's say, an apple sitting here, why is it visible to me? Right? What is the reason it is visible to me? It is visible to me because there is some light source which is sending rays streaming towards this object. And what is happening at this apple? What phenomenon is taking place which allows me to see it? What is happening here? Who will tell me this? What is happening here? What happens at the apple which allows us to see the apple? It's reflection, right? The apple is actually reflecting light towards us. It is reflecting light in all directions actually, but some of that reflected light is reaching our eye. And that is why we are able to see it. We see an object when, if there is any point on the object, that point is sending a light ray and that light ray is hitting our eye. That is the only reason we see anything. I see someone has answered. Very good, Arsha. Dikshit also, reflection, correct. Our eyes will get the reflected light. Very good. Okay. So in this particular case, we are seeing an object in reflected light. This is not a naturally luminous object, right? Like the sun is luminous, it has its own light. This apple is only reflecting light. So that was the revision for whatever we have learned earlier. Let's go further. So let us understand the reflection of light. So reflection follows two basic principles. The angle of incidence and angle of reflection are equal to each other when measured with respect to what? This is my question. Let us say that we have a plane reflecting surface, right? We have a plane reflecting surface and we have a ray coming in. It is bouncing off the surface. It is forming some angle. This is the incident ray. This is the reflected ray, right? We have the incident ray, we have the reflected ray. It is bouncing off the surface at this point. We are saying that these angles will be equal. Should I say these angles will be equal? Is this what they are telling us? Is this correct? The angle that the rays are making with the surface will be equal. Is this the correct statement? Or should I say something else here? No. Amita says no. Then what is the correct answer, Amita? Please tell me. What should I measure these angles with respect to find the correct answer? The normal. Very good. These angles have to be measured with respect to the normal. And these two angles, that is angle I and angle R, will be equal to each other at all times. At all times. Please remember that. But this raises a question. One student actually asked me this question, that, sir, why do we have to measure with respect to the normal? It's a plane mirror, right? If these two angles are equal and this is 90 degrees, then automatically these angles will also be equal to each other. What is the point of, always insisting that we have to measure with respect to the normal? What is the reason for that? Can anyone guess why we always measure with respect to the normal? Why not with respect to the surface? Anyone? Why do we always measure with respect to the normal? What benefit does it give us with respect to reflection of light? Let's answer that question ourselves. Let's say that I have an uneven surface. I have an uneven surface. I will pick one point on this surface here. I've picked this point. Let's call it point P. And again, we have, just a moment. We have an incident ray and we have again a reflected ray. Do you see the problem? If we don't measure with respect to the normal, what happens here? Are these two angles equal? If we are using only the surface to measure, will the reflection of light law be valid for the surface? If we are using the surface for reference, not the normal, will this law work in that case? Anyone? Okay, we have an answer. No, right? If we are using the surface as a reference for the angle, this law doesn't hold up, because in the case of an uneven surface, these angles can be wildly different, right? Depending on what point I choose on this particular surface, these two angles are very different now. But again, I can pick any point on any surface. Remember this, it can be plane, slanted, rough, smooth, whatever it is. I can pick any random point and I can check a ray of light hitting that point. The first law of reflection will always work, no matter whether the surface is rough or whether it is smooth. That is why we always insist that the angle of reflection and the angle of incidence are always measured with respect to the normal. That is the reason we do this. Okay. Otherwise, this law does not work. Next, the incident ray, the normal to the mirror, and the point of incidence and reflected ray will all lie in the same plane, which means that you could take a piece of paper and you could put it in such a way that the incident ray, the reflected ray, and the normal all lie within that piece of paper. If you were to shift this light source, then the reflected ray will also shift accordingly, right? The plane will change, but the plane for the two rays will always remain the same. Now, you could say, sir, this seems very obvious to us, but actually it is not that obvious. And the laws that we study for, mirrors, for convex mirrors, concave mirrors, they would not work if the second statement was not true. So remember that these are not trivial things. There is a lot of meaning hidden behind these two statements, which you will understand more in further classes. So let's move on. We have understood the basics of reflection from a plane surface. This is a plane surface, or what we call a plane mirror. Now, I have a question for all of you. We have all stood in front of a mirror. What is the nature of this image that we see from a plane mirror, like your bathroom mirror or the mirror in front of your almirah? What is the nature of that image? Do we call it a real image or a virtual image, something else? What do we call it? Two quick answers. Same size as the object, very good. Abel is telling me virtual and direct, both are saying correct answers. Archa has also said, Archa is saying it's real. Amita is telling me it is laterally inverted. Okay. So it is laterally inverted, meaning that your left becomes the image's right and vice versa. It is erect. Yes, if you're standing right side up in the real world, you are standing right side up in the reflection, but it is not a real image. It's considered a virtual image. Let's understand what that actually means. Think of it this way. If you were standing at an angle to that mirror and the light from you is going and hitting that mirror, can you put a white screen and get your reflection in that white screen? Can you see that your own image in the white screen? Is it possible? I'll just make a diagram for you to understand what I mean that by that. Let's say that you have a mirror here and this is you, right? You're very happy and you are seeing your reflection in the mirror. If I put a screen here, I just put a white cloth screen here. Will I get an image? Will I see your image here? This is my question. For a plane mirror, will this work for a plane mirror? No. Very good. It will not work. You will not see anything there. And the reason for that is that this image isn't really forming in what we call real space. Let's understand why. Why this is not considered to be a real image. If you look at a mirror, let's say this is our mirror, it's a plane mirror, and you have an object, right? Remember, whenever you are analyzing any mirror problem or lens problem, it can be any kind of mirror, it can be plane, it can be convex, concave, whatever. It can be a concave lens, convex lens, could be anything. Whenever we are analyzing these questions, you will always require two rays, bare minimum, to be able to figure out where the image is going to form, right? Always we require two rays. And also remember, these rays have to originate from the same point on the object. So if I have an object that looks like this, just a moment, that looks like this, I cannot take one ray from here and one ray from here. That will not work. So always we need a minimum of two separate rays, first of all. And the second thing is that those rays have to originate from the same point on the object. So in this particular case, we have, let's say, we have an object and I am looking at this point on the object. I need, what I said is two rays. So this is one ray, R1, or let's not call it R1. Let us call it capital R1. I don't want to confuse with small r. And we have another ray here. These are two incident rays. This is R2, right? So here we have one normal. Here we have the second normal. So again, using the first law, angle of incidence is equal to angle of reflection with respect to the normal. So here is an angle for the ray A1, R1. Here is the reflected ray, and here we have one for ray R2. So this is the second reflected ray. Looking at what we see here, are these rays spreading out or meeting together? Are they diverging or converging? If they are converging, they are coming together. If they are diverging, they are going apart. So what is happening here? What is actually happening? It's diverging. Very good. These rays are going away from each other, right? They are not coming towards each other. They are going away from each other, which means that they will never meet in real space. These rays will never meet in real space. They will never meet again after reflection, but they will meet in imaginary space. If I produce these rays backwards, let's say, along their path of travel, they will meet at some fictitious location behind the mirror. Please understand, the light is not actually coming from this point. Obviously, the light is coming from the mirror. The mirror is an opaque object. It is not going to let light go through it. But it seems to us as if it is coming from some virtual point behind the mirror. Like there's a second universe, like the multiverse of madness. There's a second universe behind your mirror and you are seeing light coming from there. So remember, whenever reflected or refracted rays, this is a general principle in optics, whenever reflected or refracted rays do not meet after reflection or refraction, right? The rays that went into the object, they're either reflected or refracted. If those rays do not meet after reflection or refraction, what kind of image do they form? Real or virtual? They are not meeting after refraction or reflection. What will they do? What will it be? Who will tell me? The rays will not meet after they reflect or after they refract. What kind of image will they form? They will form a virtual image. Very good, Dikshit. They will form a virtual image. This is a very simple test. It will work for every scenario in reflection and refraction. If the rays that you have drawn, if you are using the rules correctly, and you see that these rays are not meeting after reflection or refraction, then that is a virtual image. That is not a real image. If they are meeting in real space in front of the mirror after reflection or refraction, that will be a real image. Please keep this in mind because we are going to use this principle again and again in the slides to come. So let's move on. So what we had discussed so far were plane mirrors, right? Simple flat mirror. For a flat mirror, there is no magnification. There is no inversion. There is lateral inversion, but nothing else. It doesn't matter how far away you are. You could be 100 meters away. You could be 1 light year away. But technically, you would have a reflection in that mirror, which was exactly at the same distance behind the mirror. There is no magnification. There is no diminishing. It is the same size as the apparent size of the object. But if you were to curve the mirror, there are two ways to curve it. You could curve the mirror inward, right? So I'm curving my hand, my palm inward. So I'm looking into a cave, right? I'm looking into a cave. So in this case, this is a concave mirror. If you ever get confused about, which one is, pointing in, which one is bulging out, just remember, I am looking into a cave. I'm looking into a concave mirror. So in case just a second. So in case the silvering is applied to the outer surface and the reflection is happening on the inner surface, in that case, that is a concave mirror. If the silvering is done on the inner surface, right here, and the outer surface here is reflecting light, that is a convex mirror. So a concave mirror is curved inwards, a convex mirror is curved outwards. Concave mirrors are also known by a different name. They are also known as converging mirrors. They are also called converging mirrors. And convex mirrors are also known as diverging mirrors. So based on what I had just told you before, right, we had a lengthy chat about, what the rays will do after they hit the mirror. If they don't meet again, something happens. If they meet again, something happens. Based on that itself, can you tell me if this object has sent out these rays and they are meeting here for the concave mirror, is this forming a real image or a virtual image based on what we just learned? The concave mirror, is it forming a real image or is it forming a virtual image? This is the question. Amita says real. Hiba says real. Abel says real. Wonderful. Everyone is keeping it real. That's good. Okay, correct, right? The rays after they hit the mirror are actually meeting again in the space in front of the mirror. They are meeting in real space. If they're meeting in real space, this is a real image. What is happening in this particular case? What is happening in the case of the convex mirror? What is happening here? Are these rays meeting again after they hit the mirror? Will they meet again after that in real space for the convex mirror? No, right? They appear to meet at some imaginary location behind the mirror. They are seemingly meeting or coming from some fictitious place behind your convex mirror. So that is an example of a real image or a virtual image. The rays are not meeting again. So what will that be? A real image or a virtual? Virtual. Very good. So I hope everyone is clear on this. If the rays meet after reflection, it's a real image. If the rays do not meet after reflection, it is a virtual image. Now, there are different cases for these mirrors based on the location of the object from the mirror. Let's cover these one by one. Okay, just a quick question. Is everyone enjoying being here? Are you enjoying learning this stuff from me? Wonderful. That's what I want to hear. Okay, so there's a lot more to cover. Let's get started. So first we are going to consider the concave mirror because it is more interesting. You will see the concave mirror can behave in many different ways depending on the position of the object. Let's see what these ways are. So let's draw a very basic concave mirror. Please forgive my drawing skills. I'm not the best artist. So, okay, that wasn't that bad actually. Okay. Now, please remember that there is a convention that we are following here. I hope all of, okay, someone has asked a question. Okay. Jathaved, am I saying your name correctly? Okay, wonderful. Can you please tell us once more about virtual and real image? Fine. Okay, let's do that then. What we were discussing is, let's say that I draw a ray diagram. It can be for a plane mirror, it can be for a convex, concave, it can be for a lens, convex, concave, it can be for a simple glass slab. It doesn't matter. It can be for any scenario which has to do with reflection or refraction. It works for everything. There is a very simple rule you have to remember if you want to know the true nature of a particular image. If you have an object, let's say that you have an object, always remember for any ray diagram, whenever we are trying to find out where is the image going to be, you need 2 rays minimum coming from the object, 2 minimum, right? You cannot create a ray diagram using one. You can create a ray diagram with 1 ray, but it will not give you any useful information, right? So you need 2 rays, and those 2 rays have to come from the same point, from the same location on the object. Let's see how. So this is the object. So this is a point object. Okay. I'm keeping things as simple as possible. The point is the simplest mathematical shape you can imagine. And what did I say? In order to find out where will the image for this object form, let's say that I have a plane mirror. So here we have a simple plane mirror. Right? Simple plane mirror. I want to figure out where will be the image forming for this particular object, for this particular mirror. So what do I need? I need 2 rays minimum coming from the object, and they have to come from the same point on the object. So easy. This is already a point object. So all the rays are coming from the same place. So I draw 2 rays. I draw 2 rays coming from the object. Now, wherever they hit the mirror, we will draw a 90-degree angle to that local surface, to the local surface. I'm saying local surface, and I'll tell you why in a few minutes. So we have 2 points of incidence here. So these are 2 normals, and these are 2 angles of incidence. I will use the first law of reflection, angle of incidence, the same as angle of reflection, when measured with respect to the normal. So here we have 2 rays. So Jathaved, tell me, are these rays going to meet after reflection? Will these rays meet after reflection? These are the incident rays. These are the reflected rays. Will they meet after reflection? Don't be afraid to answer, okay? This is not an interrogation, right? We get it wrong, we get it wrong. Okay. Tell me, will they meet? Think about it. One is going in this direction, one is going in this direction. Will they meet? Think about it. Look at this. They are going like this. One is going this way, one is going this way. Will these rays meet each other again? No, right? Good. They will not meet each other again because they are diverging. These rays are diverging. And if the rays are diverging after reflection or refraction, if these rays are diverging, then the image will be virtual. The image will be virtual. Why will it be virtual? It will be virtual because The only place where these rays seem to meet, not actually meet, they seem to meet is if you produce these paths backwards and you get an intersection point which is behind the mirror. Obviously, the mirror is an opaque object, right? It is not, the light is not coming from behind the mirror, but it seems as if it is coming from behind the mirror. This is not a real point. This is a virtual point. This here is a virtual point behind this mirror. Is this understood? This is a virtual image because of that, because the rays are not meeting after reflection. Is this clear to everyone? Okay, great. Okay. So let's come back to what we were doing. We were discussing the concave mirror. The concave mirror is very important from the standpoint of your exams because it is a very, very good source of questions. Please remember this. It is a very common source of questions. It is also the most interesting mirror with regards to its behavior. Now remember, whenever we are drawing mirrors like these, we are going to have to draw a principal axis. So here we have to draw a principal axis. We call this X, and here we have X dash. So all distances from this mirror are measured with respect to the principal axis. This point is the pole, right? And this mirror is the part of a sphere. I hope all of you realize this. This mirror can be cut out from a spherical shell, correct? If I have a hollow sphere, I can slice it out of a spherical shell. Yes or no? Correct, right? So this spherical shell will have a radius. This will have a center and it will have a radius. So this distance is the radius of curvature. This is the radius of curvature. This is the center of curvature, and midway between the pole and the center of curvature, we have the focus. Midway between the center of curvature and the pole of this concave mirror, we have the focus. So we have many cases for a concave mirror. We have different behavior for each of these cases. The concave mirror will give you a different type of image for each of these cases. Let's understand. First case is the object is placed at infinity. It is placed at infinity. But what does that actually mean? What that means is that the rays coming from this object, these rays in this case are parallel to each other. These rays are parallel to each other. And because they are parallel to each other, what is going to happen is that these rays will be passing after reflection, they will pass through the focus. These rays will pass through the focus. So if the object is at infinity, the reflected ray will be passing through the focus. Another important point on the mirror is the center of curvature. If a ray of light is traveling from the object through the center of curvature, it will trace back the original path. So it will be bouncing straight back, right? It came down this way. This was the path of incidence. It will also go back the exact same way. That will be the path of reflection. So if the ray was traveling parallel to the principal axis from infinity, it is parallel to the principal axis. After reflection, it will pass through the focus. If the ray is passing through the center of curvature, what will happen? This ray will bounce straight back. The ray will bounce straight back. Another important thing is the focus. If the object, let's say, is located here, the rays coming from this object like this will all bounce off parallel to each other. These rays will all bounce off parallel to each other. So if an incident ray is parallel to the principal axis, it passes through the focus of the mirror. If it is passing through the center of curvature, it bounces straight back. And if it is passing through the focus, if the incident ray is passing through the focus, the reflected ray will be parallel to the principal axis. So I have a question. This is something that you have learned in previous classes in geometry. Where do parallel lines meet? Can anyone answer this? Where do parallel lines meet? They do not meet, or infinity, right? Actually, both of these answers are interestingly correct. Both are correct. One student said, sir, they will not meet. That is the whole point of having parallel lines, that they do not meet. Another student said that, sir, they will meet at infinity. And weirdly, both of you are equally correct, right? Parallel lines, we say they meet at infinity, but you can never actually reach infinity. And we will understand why that statement is important when we analyze the different cases. So let's look at the cases here. Please give me a moment. Okay, I'm back. Am I audible to everyone? Okay, so let's continue. So we have understood the two different types of mirrors. We understood the difference between the converging rays and the diverging rays, the difference between a virtual image and a real image. Let's analyze the different cases for this type of mirror. So these are the cases. The position of the object is at infinity. If the object is at infinity, then the image will be at the focus of the mirror. If the object is at infinity, all the rays coming from the object will be parallel to each other, and they will all be directed towards the focus of the mirror. That is why the image will be at the focus of the mirror. Remember, the position of your image is the place where the reflected rays cross each other. That is the position of your image. So in this case, if the object is at infinity, all the rays coming from the object are parallel, and after reflection, they will all converge. They will meet at the same point at the focus. So that will be your image point. So you are going to have a highly diminished, very, very bright point-sized image, and it is considered to be real and inverted. Why? If you place a screen here, a piece of paper or a piece of plastic, you will see the image of the object at that point on that screen. So any image that we can get on a screen is a real image. Now, we were at infinity first. Now we are coming closer and closer to the concave mirror. So now we are not at infinity, but we are still beyond C, that is center of curvature. If you notice in the previous case, this is the center of curvature. So we are somewhere here now. We are somewhere here. Now, you can ask, but sir, earlier also we were at infinity, that was also beyond C. What is the difference between these two? The difference is, if you take a point on this object now, the rays will no longer be parallel. Let me just clear this up, otherwise nothing is visible. Now, if the object is at the center of curvature, beyond center of curvature, what happens? If we again pick two rays coming from this object, we notice that they are not parallel now. Earlier, when the object was at infinity, they were parallel. The rays were parallel. Now they are forming an angle. So these two cases are not the same. So remember, if the object is beyond the center of curvature for a concave mirror, what is happening? The image will form somewhere between the focal point and the center of curvature, between F and C. It will be a diminished image. It is smaller than the object, and it will be real and inverted. The next case is at the center of curvature. The object is precisely at the center of curvature. It is here. In this case, if you were to draw if in this case you were to, let's just clean this up. If you select two rays here, you can select two rays here. So this is parallel to the principal axis. Tell me, where will it pass through after reflection? Who will tell me? We just discussed this. After reflection, what will it pass through? The focus. Very good. It will pass through the focus, something like this. Right? We can pick another ray, something that is passing through the focus, something like this. So this ray is passing through the focus. What will it do after reflection? What will it do? It will be parallel, right? It will go something like this. So if you were to actually draw the diagram properly with the scale, you will notice that these 2 points are coincident. They are coincident, which means that the position of your object and image are the same. If the object is at the center of curvature, your image will also be at the center of curvature. It will be the same size as the object. It is not bigger. It is not smaller. The same size as the object, and it will be inverted and real. So let's see. When the object is at center of curvature, the image is also the same place. It is the same size as the object. It is real and it is inverted. Okay. Further, when it is between C and F, so we are coming closer, right? We were at infinity. Then we reached center of curvature. Now we are between center of curvature and the focus. In this particular case, we are going to have an enlarged image, which is beyond C. So in this particular case, if we keep moving this object here, now it is here. If you draw the diagram again, the convergence will be somewhere here. It will be beyond C, and the point at which the rays meet will be something like this. So this object and this image are not the same size. The object is smaller than the image. The image is magnified, it is real, and it is inverted. We can continue doing this. We can keep coming closer and closer and closer. Now we are reaching the focus. Can anyone guess what will happen now? We have just learned what happens if a ray of light is coming from the focus. It goes to infinity. So if I keep an object at the focus of a concave mirror, can you guess where the image will form in this case? Very good. Hiba says it is infinity, and Hiba is correct. In this particular case, if the object is at focus, then we see that the image is formed at infinity. It is highly enlarged. It is very magnified. It is very, very large. It is also real, and it is also inverted. The last one is a special case. Sorry, the last case is a special case. Let's see why it is a special case. So again, here, let's clean up the house. So this is the principal axis, and we have an object that is between the focus and the pole. Use a different color. This is better. So the principal axis, and here we have our object between the focus and the pole, right? So in this particular case, what is happening? This is the one case in the case of a concave mirror where you are going to get diverging rays. You are actually going to get diverging rays. Let's see why. Let's say that we have, this is our center of curvature. Let's say that we have a ray which is passing through in such a way that it is in line with the center of curvature. So something like this. The ray is hitting like this. It is in line with the center of curvature. What will it do after it reflects? What will it do? It is coming from the object. It is aligned with center of curvature. In the same line as center of curvature, what will it do after it reflects off this mirror? Anyone? What did we learn? If the ray is coming or passing through the center of curvature, what does it do? It bounces straight back, correct? This ray will bounce straight back. It will bounce straight back along the same line. If you take another ray which is parallel to principal axis, what will it do? What will this ray do after reflection if it is parallel to principal axis? Anyone? Dikshit, give the correct answer for the previous question. Dikshit, can you answer this question? The ray is passing parallel to the principal axis. Very good. It will pass through the focus. If you were to actually create this diagram, you would notice that these two rays are diverging. These two rays are diverging. They are not meeting each other, which means what? Will this form a real image or a virtual image? If they are not meeting after reflection, are they forming a real image or a virtual image? This will form a virtual image, right? If you produce these rays backwards, they will meet at some imaginary point and this will be your image. This is not forming in front of the mirror. You cannot put this image on a screen, right? This is a virtual image. Tell me, is it erect or inverted, this image? Is it erect or inverted? Erect, right? It is right side up. Is it magnified or diminished? Is it bigger or smaller than the object? Magnified, very good. So this is erect, this is magnified, and this is virtual. This is the only case for this type of mirror, for a concave mirror, when it is going to give you a virtual image. Please keep this in mind. This is all the other cases you are getting a real image, but in this case, you are going to get a virtual image. I hope everyone understood what is happening here. Any problems? Okay, let's go. Let's move on. Now we have the image formation for a convex mirror. Now, this is much less interesting. And the reason for that is it doesn't really matter where you are standing with relation to a convex mirror, right? If you make a mirror that looks like this, which is bulging out, which is silvered on the back and it is bulging out. In this particular case, you will notice that it doesn't matter where the object is. It does not really matter where your object is. It could be far away, it could be at infinity, and it could be very near the mirror. But in each case, if you were to draw rays, you would notice that they are always diverging. These rays are always diverging, which means that regardless of wherever you place the object, it is close, it is far, it is at infinity, it doesn't matter. The reflected rays will never, in any case, meet again in real space. They will always diverge away from each other, which means that this type of mirror will always give what type of image? A convex mirror will always give what type of image? Who will answer? In every single case, it will give only one type of image. What is that? We just understood that no matter where you are standing, very good. Shiza has said, given a good answer, virtual, right? Abel is also giving virtual, Hiba is also giving virtual. It will always give us a virtual image. Then this is why you need to prepare the concave mirrors much more, because they have very different and interesting cases. But convex mirrors, you can predict. If they ask you what is the type of image, you will say, sir, it is virtual and erect, or ma'am, it is virtual and erect for every single case. This is the reason we use a convex mirror in the rear view mirror, right? If you use a concave mirror, what would happen as a rear view mirror? Would the reflection, would the image always be right side up? Think about it. This is a application question. If someone asks, can I use a concave mirror as a rear view mirror in my car? Would that be a good idea? Anyone? Very good. Shiza is telling me that we will not get a wide view because it is magnifying the image, right? Everything looks bigger, so you only see a small part of the world. What is the bigger problem? That is one problem. Very good. What is the other problem? Because the image is also, Dikshit give the correct answer, the image is also inverted. That is a very bad idea. If you are on a road, you look in the mirror and you see that the dinosaur is upside down. That is a very bad idea, right? So we are using convex mirrors for rear view mirrors because they give a smaller image. You can fit more of the world, and no matter how far the object is from you, it is always an erect image. Let's continue. So here we have some questions, and please remember these questions are all asked in the previous years. So here is one question. The laws of reflection hold true only for plane mirrors, only for concave mirrors, only for convex mirrors, or all reflecting surfaces. What is the correct option here? The laws of reflection hold true only for a plane mirror, only for concave mirror, only for a convex mirror, or for all reflecting surfaces. Simple question. I hope everyone can answer this. Option D. Very good. As I told you, the surface can be curved, straight, rough, smooth, whatever it is. Beautiful, ugly, doesn't matter. The reflection laws will always be valid. So the correct answer is option D. Let's move on. When an object is kept within the focus of a concave mirror, within the focus of a concave mirror, an enlarged image is formed behind the mirror. What will be the nature of this image? Will it be real, inverted, virtual and inverted, or virtual and erect? Which option in this case? D. Very good. What are they telling us? They are telling us that we have a concave mirror. We have a concave mirror, and they are telling us that this mirror has center of curvature, F, and pole. If they say that the object is kept within the focus, please understand that does not mean the object is sitting here. Within the focus, that is not what they're trying to say. What they are saying is that the object is inside towards to the focus. So the object is somewhere here within the focus. So this is in, this is out. Because a lot of students have made this mistake in the exam. They read this within the focus. Okay, wonderful, I'll put it here. And they got confused that this doesn't make sense. The question doesn't make sense now. So it is within the focus on this side, between the focus and pole. And in that case, we have learned that the rays after reflection will not converge again, will not meet again. They will form a erect image. It will be virtual and it will be magnified. So the correct answer is option D once more. Okay, let's look at the next question. An object is 4 centimeters in size. It is placed 30 centimeters in front of a concave mirror whose focal length is 15 centimeters. I'll say again, we are dealing with a concave mirror. It has a focal length of 15 centimeters. We have an object that has been placed 30 centimeters away from the pole of this mirror, and the object is 4 centimeters in size. So please tell me, if we look at the principal points on the axis of the mirror, if we think about the center of curvature, let's say, we think the focal point, the pole, where is this object based on the geometry of this problem? Where is the object situated? Who will tell me? Abel tells me it is at C. Dikshit also tells me it's at C. Very good, right? Because what do we know? We know that the focal length, okay, let's draw the complete diagram here. We know that the focal length is the focal length is half of this is the mirror, here is the pole, and here is the principal axis. Again, excuses for the bad drawing, but if this length is 15 centimeters, then the double of this is 30 centimeters. And according to the problem, this object of height 4 centimeters is placed here. And this distance is 4 centimeters. So the object is placed at the center of curvature of this mirror, right? At the center of curvature of this mirror. So we already know what will happen here. If you take any two rays after reflection, they will intersect at the exact same location, only inverted. So we know based on the ray diagrams, what are the characteristics here? It is real. It is in front of the mirror. You can get it on a screen, so it's a real image. Second characteristic is that it is the same size as object. The same size as the object. And what is the third thing? What is the ray diagram to show the formation of the image in this case? This is the ray diagram. Please practice this properly, and please use actual, tools for this. Please don't draw a freehand diagram in the exam. Practice it with a scale and pencil properly. The size of the image is 4 centimeters because the size of the object is 4 centimeters, right? It is not magnified. It is also not diminished. Okay. Let's move on. We have a lot of ground to cover. So now we have a different effect. We have the refraction of light. So can anyone tell me a simple definition for refraction in one sentence? If you had to explain to your younger sibling, your sister or brother, what is refraction, what would you tell them? Anyone? What is refraction? Bending of light rays. Good, Hiva. Reflection was the bouncing of light when it hits a particular material. Refraction is the bending of light. So again, let's draw a simple diagram and revise this concept. Here we have one material, and here we have another material. And the boundary between these two materials, this is known as our interface, right? So this is where one medium changes into another medium. Let's say that we have an incident beam of light. So we have a beam of light coming in like this. This is the point of incidence. I will draw a normal there. I'll draw a normal here. Now, if the speed of light is greater in the green medium and lesser in the blue medium, what will happen? It will bend away from the normal or towards the normal. The speed of light is greater in this medium, so green is greater than blue. The speed of light is greater in green compared to blue. What will happen to this ray? Will it go straight without any kind of change in its path? This is the incident ray, this is the refracted ray. Will it bend away from the normal, or will it bend towards the normal? She's telling me it will bend towards the normal. Who agrees with her? Shiza tells me that the ray will bend towards the normal. Who agrees with her? Given that the speed of light is greater in the green medium compared to the blue medium. Is she correct? Okay, Abel tells me away from normal. Amita says yes for the previous case. Anyone else? Guys and girls, please participate. It's not fun if you don't participate. Okay, the correct answer is towards the normal. Remember, if you're going from a faster medium to a slower medium, it will bend towards the normal. And if you're going from a slower medium to a faster medium, it will bend away from the normal. Please remember this. Okay, so this is refraction. It is the bending of light when light rays travel from one medium to another medium. So there are many different kinds of lenses. We have the convex lens, which is bulging out in both places, and we have the concave lens, which is bulging inward on both surfaces. The convex lens is called a convergent lens. This is a convergent lens. The concave lens is a divergent lens. So we notice here that the behavior of lenses is the exact opposite of mirrors. A convex mirror will diverge light, right? It will spread light in all directions. And a concave mirror will collect the light. It will concentrate or converge the light in all directions. But in the case of the lenses, it is completely the opposite. A convex lens will collect light. It will focus light onto a point, while a divergent lens or a concave lens will diverge the light in different directions. So we have different cases for the convex lens. Let's understand those first. If the object is at infinity, so here let's say that we have a lens, and this is the principal axis again. Wait. Let's draw this again. And here we go. And we have our principal axis. This is the optical center of a lens. Whether it is convex or concave, that is the optical center. Remember that any ray traveling through the optical center will not suffer refraction. So you could have a ray traveling like this, or like this, or like this. It can be coming from any direction, but if it is passing through the center, the geometric center of this particular lens, convex or concave, it undergoes no refraction. It undergoes no bending. The other the important case is when the incoming ray is parallel to the principal axis. So if you have a ray that is parallel to the principal axis, in the case of the mirrors, we had the fold, the focus, and we had the center of curvature. In the case of a mirror, we have the optical center, we have the center, we have F, and we have 2F. We have the focal length, and we have twice the focal length, and these are existing on both sides of this system. It has one on the left side and on the right side. The distances towards the left are considered negative. Towards the right, they are considered to be positive as a part of our convention. So if your incoming ray is traveling parallel to the principal axis, it will pass straight through the focus. It will pass straight through the focus. Please remember this. In the case of concave lenses, it is going to pass through the imaginary focus. So let's say that if I had a concave lens here, so I had a concave lens here. In that particular case, it's a divergent lens, right? It will not pass through the real focus. This ray would pass through the imaginary focus. It will pass through the imaginary focus. So a convex lens has a real focus, while a concave lens has an imaginary focus. Let's look at all the cases that we have here. If for a convex lens, please remember, if the object is at infinity, the image is at the focus. If the object is beyond 2f, this corresponds to the beyond center of curvature case for mirrors, the image will form between the first focus and the second focus, f and 2f. It will be a diminished image. It will be smaller than the object, and it will be real and inverted. If you reach 2f, this corresponds to center of curvature for the mirror case. If you reach 2f, then in the previous case, what did we have? If the object is at center of curvature, image is also at center of curvature. The same thing happens here. If the object is at 2f, the image will also be at 2f. It will be the same size as the object, and it will be real and inverted. If you keep coming closer to the lens between f and 2f, now the image will form beyond 2f2 on the other side. Remember, this is not on the same side, this is on the other side. It will be enlarged, it will be real, and it will be inverted. If it is at the focus of the lens, the image will form at infinity. So this behavior is true for both mirrors and lenses. The difference is that in the case of a mirror, the image will form on the same side as the object. In this particular case, the image will form on the other side of the lens. So it will be on the opposite side to the object. Now, further we keep coming closer and closer. We come to between the focus and the optical center. In this particular case, you are going to have a virtual and erect image on the same side of the lens as the object. So these are the various cases for a convex lens. Again, you will see that the cases for the convex lens are much more interesting and different compared to the cases for the concave lens. This is the reverse of the previous case. In the case of mirrors, the convex mirror is pretty chill. You do whatever you want. I will always form an image which is erect and virtual. But in the case of a concave mirror, you get all kinds of different cases. So it's the reverse case here. Now, for concave lens, if the object is at infinity, the image forms at the focus. But note the difference here. In this particular case, we say that the image is forming at f1. That is the focus on the left-hand side, the same size as the object. In the previous case, it was not on the left-hand side. It was on the opposite side at f2. So that means that in this particular case, for a concave lens, the image formed is virtual and on the same side as the object is being placed with relation to the concave lens. If it is between the infinity and optical center, which means that if you have a concave lens like this, and it is being placed anywhere that is not infinity, it is being placed anywhere. It can be here, here, you can keep coming closer, you can get right next to that lens. It will always be giving you a diminished virtual and erect image, just like your rear view mirror. So you can just remember that example if you ever feel any doubt as to how I will write the image formation for a concave lens. The next is the question. The refractive index of a glass is 1.5. What does this mean? What does this statement mean? So we just learned that the speed of light can be different in different media. For example, if you are going through air, the speed of light is almost the same. The difference between speed of light and vacuum is negligible. It's very, very, very small. But if you are going through diamond, the speed of light is much different. It is very, very low compared to speed of light in air or a vacuum. So we need some kind of a number which will tell us what is the difference of the speeds of this beam of light in two media. So how do we do that? So we create a new term that we call the refractive index. What we call the refractive index. What is that equal to? It is equal to, who will tell me? What is the formula? The speed of, it is the ratio of two speeds. Speed of dash to speed of dash. It is a ratio of two speeds. It is the ratio of the speed of light in a vacuum, which we write as small c, divided by the speed of light in the medium. That is c underscore m. Who will give me the speed of light in a vacuum? What is this speed that we denote as small c? What is this equal to? Is this correct? What is the, okay, Prarthana, what is the unit for that? What you have written? This is written in kilometers per second. So the value you have given is in meters per second. So always, please make sure to write the unit. Otherwise, it is not a full answer, right? Your answer is correct. The quantity is correct, but you always have to mention the unit also, right? So that is the maximum speed that light can go. You can't go faster than that speed. If you divide that by the speed of light in the medium, you will be getting the refractive index for that material. So in this particular case, we are being told that C divided by Cm is equal to 1.5. So is Cm bigger than C or less than C? Basic maths. If C upon Cm is equal to 1.5, is Cm bigger than C or less than C? bigger, right? Does that make sense? Cm will be bigger if this quantity is bigger than 1. Think about that, right? So Cm will be greater than C or Cm will be smaller than C if this quantity is bigger than 1. I want all you to think about this. Okay, tell me this. If the value of C and Cm were equal, if these two values were equal, what would be the answer here? 1. Very good, right? If both are equal. If Cm becomes bigger than C, if Cm is greater than C, will the answer be more than 1 or less than 1? Correct. So in this case, less, right? So that is the only way this equation makes sense in that particular case. Okay. This would not make sense. This would not make sense because if this was the case, then this value would not be more than 1. It would be less than 1. Okay. So remember, the maximum speed you can reach is C, that is 3 lakh kilometers per second. And all other media have a speed which is less than that value. It is always less than that value. The larger the value of refractive index, the slower light will travel in that particular medium. Please keep this in mind. Okay, so here is a question. What is a lens? A lens is a material, it's a piece of a transparent material which has been cut in such a way that one or more surfaces has been cut from a sphere. There are two main categories. We have converging lenses and we have diverging lenses. So which category will a double concave lens be placed in? So we have converging lenses and we have diverging lenses. In which category will a double concave lens be placed? This is a double concave lens. Will it be a converging lens or a diverging lens? Will it spread light or will it collect light? Okay, let's see. Let's know the answer. It's a double concave lens. So we have light rays coming in like this, right? And after meeting a concave lens, what do? They diverge, right? These rays are diverging. This is a double concave lens. So it's a diverging lens. Okay. This belongs to the category of diverging lenses. Will this lens have a real focus or a virtual focus? Will the focus of this lens be real or virtual? Virtual, right? Because these rays will never meet again. Once they are refracted through the lens, they are going in different directions, right? These fingers are pointing in different directions. The rays will never meet in real space, but they seem to meet in virtual space. They seem to meet in virtual space. So this will be a virtual focus. This is what we call a virtual focus. All right. So we have covered a lot of distance so far. In this particular problem, a convex lens has a focal length of 15 centimeters. So f is at 15 centimeters on both sides of the lens. It is a convex lens, so it's a converging lens. And an real image is forming at a distance of 20 centimeters from its optical center. Find the position of the object. Is the image formed by the lens magnified or diminished? To answer this particular problem, we have to use the lens formula. For these two problems, let's look at this other problem. Draw a ray diagram for the following cases for the formation of an image. One of the focuses of the convex lens anywhere in front of a concave lens. So the first case, if the object is placed at the focus, if the object is placed at the focus of the lens, this is F, the object is placed here, what happens? the rays will all go parallel to each other after they pass through the convex lens, if the object is at the focus. So these are the rays passing parallel to each other after refraction. So this image will be formed at infinity. For a concave lens, the matter is different. For a concave lens, it doesn't really matter where you are. For a concave lens, if you look at the diagram, it doesn't really matter where you are always going to get a virtual image. It is going to be a virtual image no matter where you place that object, right? So for the previous question, we are running out of time here. Let's wrap this up. For the previous question, we will use something called the lens formula. This is the lens formula. The lens formula tells us that 1 upon V minus 1 upon U is equal to 1 upon F. So what is V? V is the position of the image, U is the position of the object, and F is the focal length of your lens. Always remember, distances towards the left of the lens are considered negative, to the right of the lens are considered positive. Whichever quantity is unknown to us, we will not give it any sign, right? So if, let us say, the focal length of the, if in the previous case, if you look at the object here, you are asking us find the position of the object, that is U. U is the unknown in this case. So in this particular case, we will put the other values for V and F in this particular formula, but we will be giving them signs based on the location of the object from the lens. But U is the unknown quantity. We will not give any sign to U. So when we get the answer, the sign of the answer will automatically tell us the location of the object. So I hope that this session was fruitful to all of you. I wish I could have spent more time with you. This was a very responsive class. Thank you for that. And I will be discussing more topics in our next class. So I hope to see you all again. Thank you and have a great day ahead.